how electrochemistry is likely to produce some ordered mesoporous silica films with a preferential vertical orientation of mesopore channels. Actually, the ordered mesoporous materials have been discovered in 1992 by researchers of the Mobil Oil Corporation. At that time, it was silica, and the silica was obtained around surfactant templates to get some hexagonal, cubic, or even lamellar structures. And nowadays, there are huge amount of different mesoporous materials, including silica, organically modified silicates, metal oxides, carbons, metals, and so on. And they have found applications in various fields, including electrochemistry. And one can summarize the intersection between electrochemistry and mesoporous materials in 3 entries. First is the use of electrochemical methods to characterize these materials, especially the charge and mass transfer processes. Then, in turn, we can exploit the particular properties of these materials for electrochemical applications in the field of analytical electrochemistry or energy. And finally, we can also use electrochemistry to generate this kind of films. And this is exactly the topic what I would like to develop today. Focusing especially on sol-gel-derived silica films, and I will also tell you about some possible applications. So the methods that we have developed some years ago now is called the EASA, Electrochemically Assisted Self-Assembly. Actually, it combines 2 processes, the electrochemical modulation of the sol-gel process and the electrochemical interfacial surfactant templating. Actually, we start from hydrolyzed sol at pH 3 containing the tetrahydroxysilane in the presence of a cationic surfactant. And when applying a negative potential to the electrode surface, we generate the OH minus and we increase pH only at the electrode solution interface. And this induces the polycondensation of the silica. But the potential not only plays the role of accelerating this polycondensation, it also contributes to pre-assemble in a transient way some Hemi micelles at the electrode surface, leading to the growth, vertical growth of the silica around these templates. And at the end, we have a vertically aligned porous structure, which is quite difficult to get by other methods, especially the evaporation methods, which are the tendency for thermodynamic reasons to have horizontal orientation of the mesopore channels. But this is just a scheme, and I would like to show you that it is the reality. And this is the micrographs of a thin film generated on indium tin oxide electrode. As you can see, there is a nice hexagonal orientation of mesopore channels, and all these channels are oriented normal to the surface. The thickness of this film can be typically controlled between 50 and 100 or 200 nanometers. But life is not always perfect, and in addition to this nice film, we have also some aggregates that are likely to form at the top of the film, and this is due to the solution packing co-condensation of the system. But we can control the parameters, especially the concentration of the silane precursor, deposition time, and potential. And in that case, we can indeed get only the thin film without the aggregates, as you can see here from the grazing incidence XRD. We don't have any ring that we have here due to these aggregates. So now we have a membrane with a very, very high density of mesopore channels. Each pore is in between 2 and 3 nanometers in diameters. And would this film be useful for electrochemical applications? The first feature of this film is the size selectivity. If you use a small redox probe like ferrocene, it is likely to diffuse through the film to get the electrode surface, and you observe in the cyclic voltammogram a nice response due to the fast diffusion of this probe. But now if you use a bigger probe, such like the hemoglobin, which size is about 5 or 6 nanometers, it is no more likely to reach the electrode surface, and we do not observe any response. So this is a real molecular sieve film. But we can be a little bit more accurate by tuning a bit the size of these mesopore channels between 2 and 2.9 nanometers. This can be easily done by enlightening the alkyl chain of the surfactant. And if using a probe, which is a ferrocyanide dendrimer, which size is in between these two values, indeed, we can have a real perm-selective behavior, as this probe is not likely to cross the small pore diameter film, no response, and it is likely to cross a film which is a little bit larger in pore diameters, as you can see here by the nice voltammetric signal, yet lower than on the bare electrode because we have some resistance to mass transport. So we can exploit this property in designing antifouling or anti-biofouling coatings. And the first example is from our group, is the detection of a drug, propanolone, in the presence of hemoglobin. Actually, the drug is likely to be detected on a bare electrode, but in the presence of hemoglobin, we do not observe any signal because of the adsorption of the hemoglobin on the electrode surface. If working with a film electrode, hemoglobin is not likely to cross the film, but the small propanolone is likely to do so, and we can detect it. A second example is that of the group of Bin Su in China. Actually, he used the same film, but with the surfactant inside the film, and he was likely to detect the chloramphenicol directly in a wall, in a human wall blood. In that case, all the charged species cannot cross the hydrophobic barrier, and only the small hydrophobic neutral drug is likely to reach the electrode and to give the electrochemical response. A second feature is the charge selectivity. If we compare the behavior of different probes in solution, a cationic one, a neutral one, and two negatively charged one, we observe that before removal of the surfactant templates, these are the red curves, we do not observe any signal for the charged species. They are not likely to cross the hydrophobic barrier, and we have only a signal for the neutral one because it is likely to dissolve in the surfactant phase. But after removal of the template, we observe a very large signal for the neutral and the positive charge, but only smaller signal than on the bare electrode for the negatively charged one. And this is due to the fact that the silica walls are negatively charged because of the presence of the silanolate groups. And this acts as an electrostatic barrier leading to some difficulties for the anion to cross the film. And this is even worse if you work in the presence of a supporting electrolyte at low concentration, because in this case, the electrochemical double layer is much larger than the pore diameter, and we have a total overlap of these layers, making that the anions are not likely to cross. And one needs to increase the concentration of the supporting electrolyte to start to see the response of the probe ferricyanide. Because in that case, in very high concentration of electrolyte, the electrochemical double layer becomes much smaller than the pore diameters, and now the anions are likely to cross. So we can play with the ionic strength to modulate the rate of transport of the anions through this film. And another way to tune this is to play with pH. And I show you the case of a bulky polyanion, which is a polyoxometallate, which even in the presence of a high ionic strength gave rise to a very small response with respect to the response to the bare electrode. But now, if we work in a very acidic medium, in that case, the silica surface becomes positively charged because of the prostronation of the silanol groups. And in that case, the bulky polyanion is likely to cross and also to be accumulated in the film. So by changing pH or the ionic strength, we can tune the permeability of the film through the anions. If the anions are rejected, the cations can be accumulated and pre-concentrated before their detection. And I show you here the example of the detection of an herbicide, a decationic herbicide, which is paraquat. And as you can see, we observe an increase in sensitivity by more than 100 of magnitude if using the Mesoporous silica modified electrodes in comparison to the non-modified electrodes. This is due to the accumulation of the positively charged species to the negatively charged film. and we can apply this sensor to real medium analysis. These are the results that we obtain from a sample of the Meuse River in France and in Belgium, actually, which is characterized by a rather small ionic strength. And if we spike this river sample with paraquat, we observe in the nanomolar range a clear response of the modified electrodes, but not response on the bare electrode. And the detection limit was 12 nanomolar, which is above the maximum permissible level for this, this particular analyte. So these are some applications for the non-modified films. And if one would like to enlarge, to increase the possibility of application, we would like to functionalize this film. And as far as functionalization of silica is concerned, usually we use an organo-3-alkoxysilane. But if we try to use this for grafting our particular films, it led to some pore blocking effects. So we cannot use post-synthesis grafting. And if you use the co-condensation with this organosilane with the tetra-alkoxysilane, actually it works, but it is limited to a certain amount of organic groups. And this is illustrated here for the functionalization with amino groups. And above 10% of organosilane in the medium, we lose the very good organization of the film. So one needs to find another way. And the other approach that we have used actually is a combination between the electro-assisted self-assembly co-condensation approach with the click chemistry. So we need to check if these two steps are likely to occur. The first one is the co-condensation of tetra-etoxysilane with the azide organosilane to get an azide-functionalized film. So we need to check if it works by our technique. And then if it works, we could exploit these azide-functionalized films in a click chemistry by using the Huygens reaction, by allowing to react the azide with an alkyne functionalized system, and I will give you the example of the ferrocene system. And the answer to the both questions is yes. We can form this kind of film with an hexagonal orientation of mesopore channels. The orientation, vertical orientation is maintained, and this is maintained up to 40% of the organosilane in the medium, which is quite high. And this is explained by the stabilization effect of the zwitterionic azide with the negatively charged silica surface and the positively charged surfactant. And once getting these functionalized with azide group, we can exploit this azide group in the Huygens reaction to bind some ferrocene groups. And as you can see here, by increasing the amount of azide group, we can increase the amount of ferrocene group in the film. And these ferrocene groups are electroactive. And we observe intensity in the cyclic voltammogram, which is directly proportional to the amount of ferrocene in the material, down to 2.5% of ferrocene in this film. Below this value, the ferrocene are still in the film, but due to the insulating character of the silica, the electron transfer mechanism is electron hopping between adjacent ferrocene moieties. And if these ferrocene are too far from each other in a very dilute film, we do not observe any reaction. So with this kind of film, we can expect to observe some long-range charge transfer through the insulating silica layer. And we have proved this using, again, this ferrocenyl dendrimer, which is size-excluded. So that means that in the absence of this dendrimer, we should observe only the electrochemical activity of the ferrocene moieties bonded to the surface. And in the presence of this, we could observe a larger signal. And this is indeed the case. As you can see here, in gray, this is the response of the ferrocene inside the film without any dendrimer. With the dendrimer, we observe an increase in this color. And this increase is as large as the potential scan rate is small. So it means that the electrons would need some time to transfer between the electrode surface and the top of the film. And if we enlarge a little bit this, we can observe that this increase in current corresponds almost to one ferrosinyl group. This system on bare electrode will transform all the ferrosinyl groups, all the 9 ferrosinyl groups, because of fast electron transfer. If transferring the electron through these insulating films, we transform only one ferrocene group. But it works. We can have some electron transfer in isolating membrane, even if it is slower than directly on the top of the electrode. Checking that the oxidation of ferrocene would need the charge to be compensated by an anion. And taking this in mind, we could try to develop an indirect amperometric sensor for anions. And indeed, this is the case if you use a flow stream of only water, and if you inject some concentration of an anion, nitrate for example, you observe first a capacitive contribution to the change in the conductivity of the system, and then a Faradic contribution, which is due to the oxidation of ferrocene, which charge neutralization by this anion. And this is what you observe with the film electrode. On the bare electrode, of course, you have only the capacitive contribution. So it works, but the problem, as you can see, is that we observe a decrease in sensitivity because we consume the ferrocene groups during this detection. And a way to overcome this problem is to work not by simply applying a constant potential, but applying a differential potentials, yet quite large, and which is just not so common in electrochemistry. And in that case, we oxidize the ferrocene, we reduce the ferrocenium, we oxidize the ferrocene, and so on. So that means that the response can be constant and very reproducible from one experiment to another one. And this peak 8 is directly proportional to the concentration of the nitrate, which is an advantage in comparison to the classical potentiometric sensors, for which the response is directly proportional to the logarithm of the concentration, which is not likely to follow a very small variation of concentrations. We can also apply these new detectors as an electrochemical and amperometric detector in ion chromatography. I illustrate this for the separation of some anions here, fluoride, chloride, bromate, nitrate, sulfate, and phosphate, and compare the response to the classical conductivity detectors. The electrochemical cell was not optimized, so we have some noise, but as we can see, we can get even more larger intensity with the amperometric detector in comparison to the conductivity one. And just to finish, we could also exploit this kind of redox-functionalized vertically aligned film in the field of energy storage as new pseudo-capacitive materials. And the first example is a planar film deposited on a transparent indium tin oxide electrode. As you can see, the transparency above 80% can be maintained even after deposition of the film containing these ferrocene groups. And thanks to the fast electron transport by electron hopping, we can get some charge and discharge curves. But for improving the capacity of these materials, we can also electrode deposit these kind of films in the porosity of highly porous films made, for instance, of graphene oxide. The graphene oxide can be obtained by the exfoliation of a graphite electrodes, for instance. And as this deposition method is applied only on the conductive part of the electrode, it can be deposited quite uniformly in the porous structure of the graphene oxide. In that case, we also observed fast charge transfer processes. Almost all the ferrocene groups can be exploited. We have a typical surface-controlled behavior in electrochemistry, and this leads to quite interesting rate performance for this electron hopping material for energy storage. So I hope that I convince you that electrochemistry is quite a simple way to produce mesoporous silica films with a preferential vertical orientation of mesopore channels, which is quite difficult to get otherwise. Actually, we could deposit this kind of film of various kinds of conductive surfaces. These films are display some permselective properties. They can reject anions and accumulate cations, and also reject some big species and allow the small one to permeate the films. If we combine this electro-assisted self-assembly method to Electrochemistry, we have a versatile platform for getting functionalized film with various different functions. I just show you the example of ferrocene, but you can modify it with a huge amount of organic groups. And when incorporating redox-active groups inside this insulating film, they are still electroactive, working by electron hopping, and we can exploit this, for example, in electroanalysis for the indirect amperometric detection of anions, but also for energy storage application. Then I will end up by thanking people who worked with me in that field. The story started with Mathieu Etienne on silica modified electrodes. Then Émilie Sibotier developed this mechanism of vertical growth. The optimization was made by Aurélie Gou. All the analytical applications were made by Tokir and Cheryl, and all the functionalization was developed by my colleague Neus Fila, who is expert in molecular electrochemistry, and the energy aspects were developed by Dion Ren Wang. So I thank you very much for your kind attention.